to add some numbers to a total, we do it concurrently. We can add a wait group where we say, hey, we're going to spawn 10 go routines, and let's wait for all of them to complete before we continue. So this wait call will actually be blocking the execution of the print of total. Cool. So let's see how we can put this together to give you guys an example. So a very common pattern is typically, you have your main function, you're listening to something coming from a channel. And in this example, we're basically creating this background routine called generate powers of 2. So essentially every second, we're going to be pushing the power of 2 over a channel. And in the main routine, we're going to be consuming that, right? So there's a very popular time package that exposes the ticker function. You can do a lot of really cool stuff, but in this case, we're waiting to receive something from the ticker, and we're going to be pushing to another channel with the result. So essentially, Go lets you create these programs where you can have all these different things happening concurrently, independently of each other. In Go Ethereum, for example, you have the transaction pool listeners, you have the peer-to-peer networking service running, you have the blockchain processing, you have the miner enabled. So you have the ability to really launch these pseudo processes, and they're kind of like daemons that are running and always doing work, and you have full control over them using Go itself, which is very powerful. So one thing is, channels, which are a method of communication across Go routines, can take an optional value called the buffer size. So what this is, it's essentially telling me, how big can this channel get before it gets full. And what does it mean when a channel gets full? When a channel gets full, it means that when you try to send over it, it's going to create a blocking call. So if, in the first example here, I create a channel and I'm trying to send over the channel, well, I cannot send over it because it's practically it's full because it has a buffer size of 0. So unless there's something waiting to receive the data from the channel, it's going to be blocking the thread. In this case, you're going to get an error because the main thread is pretty much blocked. There's nothing happening, and what it says is fatal error. All Go routines are asleep. You can actually make a channel buffered, which means that you give it a size. When you give a channel a size and you send over it, the send is non-blocking. So meaning that if I have this second example, I have a buffer channel of size 1. I send the value 3 over the channel. There's no issue because the channel has the capacity to accommodate one item before it starts blocking sends. If a buffer channel is full, however, and you try to send something over it, then if you're gonna try to send something over while it's full, you're gonna get the same error as you did if the channel were unbuffered. So in a nutshell, it's very tricky and it's very tempting to kind of want to give channels really big buffer sizes. They have different use cases and different situations where you might want that, and we're going to go over some of those examples today. But in a nutshell, you want to be careful. Essentially, when you send over a channel that is unbuffered, you need to make sure that there's something listening for that receipt. There needs to be a listener ready to receive something if you're sending over an unbuffered channel. So they're the best option in most use cases, and most of the time you don't really need a large buffer. So one works as a default in many examples. Unbuffered channels help as a way to limit execution, and we're going to go over that today as well. So as mentioned, if you're using an unbuffered channel, you should always make sure there's a listener ready to read data that's being pushed over the channel. So what does concurrency look like in Go Ethereum? And I guess what are some of the things that how is it used? And what, sometimes when you open Get and you look at some of the code that's in there, you see these files with hundreds of lines, all sorts of crazy stuff with channels, Go routines, wait groups, like what's going on, right? There are a few particular use cases, and I say this summarizes most of them fairly well. So the first one is concurrent computing of expensive operations, right? So an example is, we're trying to hash this tree, and we could do it sequentially, but essentially we could actually also split it up and launch a Go routine for every single one of the children. And as you can see, we have a wait group here so that we can make sure that all of them complete. So we're spawning these 16 operations concurrently and performing this hashing operation this way, helping us get some speed up in some situations. Another case is asynchronous data retrieval. So a very common one is, you want to start some sort of fetch procedure, like, hey, give me some of the headers by hash, and you specify some sort of range. And then you spawn a listener using a select statement where you're waiting to receive data from this routine that you spawned, right? So it's a fairly straightforward way of kind of triggering some work. You don't know how long that work is going to take, but you're ready to accept the results at any time. Another common use case is an application internal PubSub. So Ethereum has this event library, which is really cool. Essentially, it creates this feed, send, subscribe model where you can kind of send some data to some feed, and anyone can subscribe to that feed and get the data. So it's very useful inside of Ethereum to communicate between processes. So as an example, when in the blockchain package, when you receive a block, it becomes very straightforward to kind of just to send that out to a feed. I don't care who's listening, and other services inside of Ethereum can then subscribe to that. Like for example, maybe there's an RPC service that's listening to streaming, the latest chain head. Maybe there's some P2P requests. So it's very useful. We use that as well in ETH2. The event feed kind of PubSub internal model is super helpful, and this is all implemented using concurrency and channels underneath it. So you'll hear a few things, especially if you have used concurrency a lot in Go, and it's important to understand kind of what these things really mean. I heard these all the time, and I didn't really understand their ramifications until you feel their effects in a production application. So three things. The first one is from Rob Pike, one of the basically head honchos of the Go programming language. He is instrumental to the creation of the language and to its current development. So Rob says concurrency is not parallelism, right? So what does that mean? If you recall at the beginning of the talk, we said that concurrency is just the ability to deal with multiple things happening independent of each other. I never said that these are things happening simultaneously. So essentially, background routines, I/O operations, executing different things in a single program. Whereas parallelism is about running things at the same exact time. I think most of us have multi-core computers at this point. A lot of the times, those computers, the operating system has very smart ways of parallelizing some operations, maybe some math, for example, right? Let's say you're doing vector dot products, that stuff can be parallelized, meaning that you have two cores, two processors, and they are running the functions at the same exact time because they are actually concretely different in physical space. So here's what Rob Pike says. He says concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once. They're not the same, but they're related. Concurrency is about structure. Parallelism is about execution. Concurrency gives us a way to structure a solution to solve a problem that may not necessarily be parallelizable. So that means that concurrency works even if you only have a single, even if you only have a single core in your computer. If you only have one processor, concurrency can still happen. It just, it's up to the Go runtime and the actual computer to figure out how it's going to allocate time for each of those background routines to execute and work, right? So it's very important. A lot of people think that, hey, I'm going to parallelize this work by using Go routines. But you should think very carefully about if that's what you're actually doing. Something else you'll hear quite a bit, and this is actually extremely important, is people say that in Go you should share memory by communicating. What does this mean? It means that it's very tempting to access resources, shared resources with Go routines using, for example, log-protected globals with immediate text. So for example, let's say that I have a list of transactions, right? And have multiple Go routines that are reading and maybe writing to this list. I need to make sure that there are no race conditions around access. I need to make sure that they are protected with a lock. Only a single accessor or writer can acquire the lock and then be able to mutate this data structure. When you do this, you have to deal with a lot of extra complexity around data races, invalidation, deadlocks. Not only that, but the more code you write, the more potential bugs are going to pop up. So let's look at an example, right? So say here we have this like polling approach. Maybe we're doing some URL polling with HTTP. And you kind of have this resource where you keep track of kind of what you're polling, right? If you use mutexes and logs, look at like how crazy your code becomes, right? Not only, you have to lock the resource access to make sure that only one can access it. You also have to keep track of kind of what's currently polling. You have to have the check of like when is the last time you polled, and then you have to release those resources and unset some properties, right? So this is very bug prone. It's very easy to shoot yourself in the foot using something like this. You might forget to unlock the mutex and then you don't realize it, and then you end up having like a deadlock in your production application. So it doesn't mesh very well, and it's tempting because it's easy and it's available for us to do, and it's kind of fairly intuitive, right? Like, oh, we have this shared global. Let's find a way to split up access and figure out where to go from there. It's tricky and bug prone, right? So let's take a look at pretty much the same functionality using channels. So we communicate information instead using channels instead of dealing with shared resource access, right? So in this case, we have a channel of resources we want to pull, and then we send out the result via some outbound channel, right? We have pretty much the same logic. We don't have to deal with the potential bugs and deadlocks of using mutexes. There's a smaller code footprint. There's no excessive mutex locking and unlocking to achieve the same exact result. And as we'll see later, channel communication actually ends up being extremely efficient at the program, at the Go runtime level, because it does a little bit of magic in terms of how Go routines are scheduled. So it's very powerful. And this is what people say, like share memory by communicating. Don't communicate by sharing memory, right? A final thing that one other mental model that I'd like to explain, and it's very important, is when I see this a lot, I guess, and new Go developers tend to do this quite a bit. But you should leave concurrency to the caller, right? So exposing concurrency details to API callers creates ambiguity. And by API, I don't mean REST API, I mean any sort of programmatic API that you expose. It can be like a public method of your library. You want to decide, let the caller figure out how they want to use concurrency. It's very easy to wrap asynchronous operations in a synchronous way, and you can actually make concurrency an internal implementation detail of your work, right? So let's take a look at an example here. So say we have this function called fetch HTTP, and it's coming from some library that I can use. It returns a channel with some data, and it takes in a URL and some context. So when you're looking at this for the first time, say you just have the function signature, you ask yourself, how does error handling work? What happens if we have a buffer, or if this channel is buffered or unbuffered? How big should the channel buffer be? How does context cancellation work? You have all these questions, and you're forcing the caller of this to kind of figure out these decisions, and where they probably shouldn't. If you instead refactor it and you do not expose the internals of concurrency, it's very simple. There are no questions asked. So if I just tell you, hey, I have this function called fetch HTTP, you give me a URL, I give you some data, that's very straightforward. It's very easy to make concurrency an implementation detail. In the former expression here, we have this function called crunch numbers async. So for example, we have this channel where we have a channel with a buffer channel, we pass in some result, and then we return the channel. Then the caller has to figure out how to deal with that. They have to maybe create a select statement. They have to do some crazy stuff. Whereas in the latter, the internals of the function are using concurrency, but the function itself is synchronous. And from a caller perspective, it's very straightforward. So which one is easier to deal with? I think it's fairly straightforward. So I would urge you guys, if you tend to expose channels as return types and maybe public public methods, to rethink if that's really what is easiest for your callers. So let's take a look at a bit more about Go routines, and I guess more about what are some of the things that really matter about their return. So Go routines are cheap, but they're not free. At the time of this presentation, they take approximately 2 kilobytes of stack size at a minimum. I believe this was reduced by quite a bit in the latest Go version. But Go routines are a runtime abstraction. They're not operating system threats. meaning that they're like managed by the actual Go runtime in the application layer. They're, you know, and that runtime scheduler actually cooperates with your operating system to figure out how to schedule things intelligently across threads. So if you guys can look here at this diagram, we have the Go runtime, and kind of like, you know, it's this box where your application is running. The scheduler is managing a bunch of Go routines and figuring out, okay, Go routine 1 needs to run right now, Go routine 2 needs to run afterwards. You know, I have space for Go routine 3 in between them. So it figures that out, you know. And how does it figure that out? Well, it actually, you know, it's intelligent by cooperating with the operating system scheduler itself to figure out, well, look, you know, we have you know, our computer has 4 cores. We can actually try to give these Go routines, you know, their own, you know, kind of like their own thread in a way. So it's a very smart cooperation going on that the application developer doesn't really need to know anything about, and it just works. So what is the difference between Go routines and, let's say, something like threads, which are common in other programming languages? So Go routines can perform a lot better because there's no need for preemptive scheduling, right? So what is preemptive scheduling? So preemptive scheduling means that your operating system actually has to stop things every few milliseconds or less than that to figure out, okay, we need to schedule a thread for some operation, right? Go routines, since they're happening at the application layer, there's no need for this to happen, right? It actually, there's a lot fewer stop the world operations that need to occur for Go routines to work properly. They consume far less memory. They're actually 2 kilobytes, and basically like stack allocations. And it's easy to spin up tens of thousands, right? It's very common to have applications that have at least 10K Go routines. You can go even up to 1 million if you want to, and you know, you will still probably perform really well. Lifecycle of Go routines are managed by an abstraction. So it's a runtime abstraction called this runtime scheduler, and it reduces the needs for operating system calls. Threads. So threads are these low-level primitives that are optimized by the operating system and the process scheduler. Right? So they're pretty low level. They're pretty much, you know, very close to your computer's, you know, processors, and kind of like and basically are scheduled into the cores of your computer more directly by the operating system. They need a lot more work to use them because of how many threads you can reasonably create. And threads can be blocked by system calls and things that are outside of the control of the application developer. You know? Like if you're writing an application, it's really nice to not have to think about the internals of what kind of computer it's running on. When you write Go code, for example, it really doesn't matter what kind of architecture you're running on because concurrency is more of an application abstraction rather than an operating system detail, right? You know, I don't have to think about maybe quirks between running on, say, like a flavor of Linux versus like Windows, for example. And no need to think about particular things. Oh, you know, my computer only has, you know, it's only single-threaded. My computer has 4 cores, 8 cores, whatnot. Go routines are, you know, the runtime scheduler is very smart. It cooperates really well with any type of operating system scheduler, and it's just a very powerful construction. Right? So, like, let's look at, like, I guess how context switching happens in threads. So, in a traditional thread model, there's a lot of overhead because, say that you're executing something on a thread, then, you know, there's another message on thread 2, and then you need to switch back to thread 1. Basically, the operating system has to do all this context switching. It has to figure out, like, okay, I need to run this on thread 1, then I need to switch it to thread 2. This costs significant overhead if you're doing it quite a lot, and it's something that can affect how your application is actually running. So when you write programs that use threads, you need to keep this stuff in mind, you know, and what comes to mind is developers end up creating some abstractions themselves. They end up creating things such as thread pools to improve upon this. These are things that honestly should go under separation of concerns. For the Go routines, this is actually not a photo, not a diagram of your operating system, but more like the Go runtime scheduler. It's different. Context switching happens at the application layer. So this is happening actually in the Go runtime, not in the operating system. So we do not lose significant overhead to thread switching from the OS scheduler in this case. The Go runtime still needs to figure out, okay, Go routine 1 needs to run here, Go routine 2 is ready to run, Go routine 3 is idle, waiting. So all that happens at the application layer, which is a lot cheaper than underlying, for example, operating system operations. So the Go runtime scheduler. So with Go routines, the same OS threading core is being used for the processing. The OS thread does not go into the waiting state. So like we said, in the actual operating system thread, we end up having more overhead because sometimes the thread goes into a waiting state, and that's the system call. Go runtime then turns basically I/O work that the OS would normally do with context switching into CPU bound work, so that your operating system does not have to do all these like switching operations underneath the hood. So we avoid overhead at the OS level. It's basically what we want to get at. So something that I think is really important and relevant, and something that people always, I guess, might be, are concerned about is why concurrent code is not always faster, right? I've had people say like, hey, like, I had this really fast algorithm, and I wanted to squeeze out more speed from it, so I added concurrency. It became like 3 times slower. Like, what happened there? So that's kind of like why this prior context comes into play. So I guess the question that I ask myself is, how much is too much scheduling? I know that the runtime scheduler does some work. I know that it needs to do some work, especially if we have like millions of Go routines, right? So I guess how much is too much? How much is it until it has a noticeable effect on your application? So it depends on the workflow that you're doing. So are you doing CPU heavy work or IO heavy work? There are a lot of caveats in using concurrency to speed up your application, right? We see a lot of kind of beginner Go developers want to, hey, I'm just going to use Go routines, wait groups, and whatever to speed up this for loop that does this, this IO operation, something like that. Too much Go routine scheduling can incur a speed penalty, but also some unintended consequences. Cool. So just to clarify again, the overhead of Go routine scheduling depends heavily on your type of workload. If it's CPU bound or IO bound, and how many cores you have on your computer. So here's an example of a CPU heavy workload. I mean, this is like very, very trivial. We're just doing a lot of like, just like number crunching, like array operations, slice operations. So we have bubble sort in this case. We have this list of integers, return the same list, but sorted, and just crunch through it. This is an inefficient algorithm. It's pretty heavy on, if you pass in a very large list, it's going to end up being pretty heavy on your CPU. So an IO heavy workload is when you're actually doing, for example, system calls and disk operation. So a common one is like, let's say, hey, I have a directory of CSV files, and I want to figure out if there's this header string in any of these files, right? So like, okay, cool. So we're going to read all the files in the directory. We're going to then, read the CSV file itself, and we're going to check if the CSV data contains the header, right? So very, very straightforward. The crux of the operation is going to be actually opening the file and reading it, and reading the data on marshalling, for example. You're actually going to have to do disk operations, and a lot of your throughput will be bound to how fast can you actually read from disk. Right? Imagine that we have millions of these. We have files that have millions of rows, for example. So there's some optimization for this, like a naive implementation. But that's an example. Just IO heavy workload, CPU heavy workload. Right? Other CPU heavy workloads are things like number crunching, like you're doing vector dot products. So CPU-bound workflows, they need parallelism to benefit from concurrency. So what this means is if you're crunching numbers and you're doing CPU-heavy work, let's take a look at a few examples, right? So say you only have a single core and you're doing sequentially, your results will be as fast as normally you can do them. If you have a single core and you're doing concurrently, you have a slowdown because essentially, you have the overhead of the Go runtime, Go routine scheduling, context switching in a single core in a CPU-heavy workload. If you have multiple cores and processing concurrently, then you'll observe a speed up. As you mentioned earlier, the Go runtime scheduler is very smart. It's able to do a lot of very, very interesting interactions with the operating system scheduler to figure out how to split up the work. But yeah, basically CPU-bound workloads really benefit from parallelism. So if you have a very big and multi-core computer, using concurrency for your CPU-bound workloads is very helpful. IO-bound operations actually perform better concurrently, even in single-threaded machine environments. Because there's no thread context switching, there's only application-level context switching. Go is able to efficiently use a single thread throughout the entire application. So like if we were to make our CSV reading concurrency operation, we would end up seeing a skew because of the way the Go runtime deals with system calls and because of how the Go runtime deals with IO bound operations. So it's very powerful. So just keep that in mind. In Go Ethereum, for example, or in Ethereum, you're going to see a lot of IO heavy workloads, which is why you see a lot of examples where the Go Ethereum authors, they end up using concurrency to speed up some of this. They don't use it excessively, but they know exactly when to use it and they know when it makes sense. So I guess one thing I want to add is very important is try to optimize the fundamental type complexity of your algorithm before you add Go routine magic. It's very tempting that the first thing that you want to do is you have this function, you observe that it's kind of slow, it uses a lot of maybe heap allocations. The first thing you want to do is like, oh, I'm going to use wait groups and use workers and split them up and make it parallel, even though it's not parallel. So yeah, try to go back to the fundamentals first. It's very important. I think that it's very easy to forget that you're getting overhead from the runtime scheduler by adding excessive Go routine magic to your application. So that's one takeaway that we want everyone to kind of keep in mind. Great. So I guess a real world example now of putting things together, and I would love to showcase this, is an in progress cache. So we'll do some live coding here, but what's the problem here? So let's say we have n callers simultaneously ask you to perform an expensive operation. So we want to avoid our code having to do the expensive operations n times if one is already in flight. So I'll give you guys an example. So let's say that in E2 we have this expensive operation that has to do with processing what we call the beacon state, which is the state of the beacon chain. If we have 1,000 operations trying to transform that data at the same time, we want to avoid that because not only is the operation slow, it also incurs significant performance overhead on our CPU and RAM. So maybe you might have 10,000 calls, right? So like, how do we build something like this? How do we solve this problem? This is actually something that is very common in things like Ethereum, and a very common problem that you'll encounter. And there's a pretty good solution that we can use using some of the things that we learned. So what do we do here? Okay, I will transition now into presenting the actual code. Can you guys see my screen, the code?
Yep, we got it.
Okay, great. Is the size of the text good?
Seems like it.
Okay, excellent. Thank you. Cool. So we have this. Let's start here. So essentially, okay. So we have this main function here, and what we have 5 workers, or basically 5 callers, right? So what we're doing is we're saying, hey, like perform 5 expensive operations. Expensive operations concurrently. Cool. So we have this function called perform expensive work. So what we're doing is we're saying like, hey, do some expensive work, and it's going to take, let's say, 1 second, right, just to simulate a real application. Right? So if we run this function, we're going to see that all 5 workers are doing expensive work. We want to avoid this. Let's say that, like, imagine that this perform expensive work function takes up like a few megabytes or something of heap. It takes up a lot of your CPU. It's expensive. It might take 2 to 3 seconds or more. We want to avoid doing that expensive work. And it's very dangerous. Imagine that you might have 1,000 callers. It's not rare to have like maybe even 5,000 callers in, like, for example, in blockchain applications doing something like this. So where do we start, right? Like, what do we do? And that's when, like, some of the really cool patterns that pop up around channels and buffering. So the first thing that we can do here is we actually want to, let's say, queue expensive work to happen. So what we want to do is we want to make sure that, okay, the first worker that gets in, we're going to queue work, but all the other workers are going to have to wait for that worker's work to complete. So let's think about it this way, right? Something that we can do here is we can create a channel. We create a buffer channel. we're gonna call it, we're gonna create this global one, we're gonna call it maybe, we're gonna call it, let's say, stopper or something. There's no more technical name. This is technically a semaphore, but for the sake of this, we'll just call it stopper. So we're just gonna get a simple channel with a Boolean, and we're gonna say stopper is a channel with a size of 1. Basically, we only want a single operation to go through before all others block. Cool. So we have the stopper channel. So what we're going to do here is we're going to say, okay, I'm going to create a new function, and we're going to be calling it schedule work, right? And we're going to pass in this, we're basically going to say, stopper channel, hey, I'm going to schedule some work. Notify the stopper channel that we are doing expensive work. Okay, great. So that's the first step. The next step we're going to do is we're going to actually perform the expensive work, right? Okay, cool. So what's going to happen here? So what's going to happen here is we're going to be, when a worker initializes working, we're going to send a notification over the channel, and all the other, and then one is going to go through. So the first worker is going to go through line 34, and it's going to start performing expensive work. All other workers will be blocked. So all of them will be just stopped. They will not even make it to line 34. They'll be stuck here because the channel is blocked. So that's kind of what we want to do first. The next thing I want to do here is we want to actually notify all workers that work has been completed. So something that we're going to do here is we're going to make our expensive work function return some value. Is there an error? It's going to make it return 0. And what we want to do here is we want to say, okay, we have the result of our expensive operation, and what we want to do is we want to notify all workers that work is complete. So the next thing we're going to do here is we're going to create this global. Let's call it like listeners, and these are basically the workers that are listening for a result. Right? So we're going to be sending the result over to every single listener. We're going to notify all workers that their work is complete. Cool. So we're going to register then. We're going to register these listeners. And let's say that the max capacity of this list is a number of workers. Okay. So we're gonna have some listeners here, and it's gonna be a slice of channels. So what we're gonna do here is we're gonna say, okay, I have a worker and I have a result that I want to receive. So let's say let's call it a result channel. Let's see, we don't even need this. So what we're gonna do here instead is we're gonna say, okay, I'm gonna append this result channel to the listeners list. Cool. And then after that, I'm gonna be waiting to receive a result here. So and I'm going to say something like worker D, worker index received result. So just to reiterate here, what we're doing is we're saying like, hey, I'm gonna schedule some work, and I want to wait for a result to be received from that scheduled work, right? So I'm adding the worker to the list of listeners, and then we're gonna make this schedule work function concurrent. So we're gonna add a go keyword here. Cool. So essentially, let's go back to this function. We're notifying that we're doing some expensive work. So only one guy will go through. He's gonna perform the operation, and then the result will be broadcast to all the workers so the work is complete, right? So one last thing that we need to do here is we actually want to close this channel. So you should always remember to close your channels. It's good practice. There's a close language primitive that you can use. It just helps keep things neat in case things go wrong. Cool. So let's take a look here. Let's see kind of what's going on. And we should only be seeing okay, there we go. Cool. So if you guys can see that we queued 5 expensive operations concurrently, and only worker 4 was doing work, expensive work, and then all the others were queued waiting for a result. And then all of the workers kind of receive their response. If you look carefully, we only did one of the expensive operation, even though we might have had 1,000 callers, 10,000 callers, right? If you profile your application, you're only going to see this perform expensive work function being performed once. And what is the key here? The key here is that we use a buffer channel as a stopgap to prevent and limit concurrency for the other workers. So in this case, for example, we made sure that only one worker can go through, the rest will block, right? In this case, you can think about the stopper channel as a semaphore. This is technically a semaphore, which is a term from computer science, and essentially it's a way to balance concurrency. So that's pretty helpful, and it's very straightforward. If you were to implement the same logic using prefixes and things like you need to keep track of like what requests are in progress, you need to add like a new text around like logging work. It's tricky, right? So like once again, we're combining everything we talked about today, where we are sharing data by communicating, not communicating by sharing data. We are leaving concurrency to the caller, and we are just using channel primitives as best as possible in a very simple way. So this pattern comes up a lot in core development. We use in progress caches significantly in Prism. I'm not sure how Ethereum leverages them, but I'm pretty sure that they also have some model of this. Semaphores are very powerful, very very common. So yeah, that's happy to share this code as well if you guys are interested. But that's pretty much it. I'd love to open it up to questions, comments, and yeah.
Yay, thank you very much. Well, we're running a little short on time, so I think we got time for maybe 1 or 2 questions if anyone has them.
Sure.
Mark.
Okay, so my question is, do you know of any good examples of using sync.conf in practice?
Yeah.
Cool, yeah, that's like...
Yeah, absolutely.
That's the one, just like going through the sync package, I've been on the hunt for a good example of how that works, like really grok it.
Sure, yeah. See that, so I think there's some echo.
Oh, hang on.
Yeah. Okay, yeah, so sync.conf is a very popular package from I believe it's from the standard library. Yeah, so it's from the sync package in the standard library. I would recommend you take a look at the Go Ethereum events library because they use sync.conf to basically do some advanced operations on channels. So basically every time you're doing like meta programming around channels, so like for example, managing select statements programmatically or something like that, you want to use sync.conf. It's mostly for meta programming. Libraries that like provide wrappers around concurrency typically use sync.conf. I'd say like as a normal user, you're not really like going to use that unless you're actually writing some helpers or something like that. So yeah, I don't think it's something that typically people should need to worry about. And if you need to use that as a developer in your application, there might be a different approach that is easier.
A follow-up on that, I don't know if you know, but off the top of your head, does sync.conf on use operating system CVARs, or do they hook through the Go runtime before potentially hitting the operating system?
Yeah, good question. Actually, let me check really quick because I can easily pull that up. That's a good question. Yeah, they do use, yeah, they definitely use operating system calls because that basically does low-level interactions with telling the, the scheduler like, hey, you need to wait for the condition to occur. So you need to actually, they actually use a runtime package to perform the operation. Yeah. Well, thank you guys. If there's any last question.
Yeah, probably a lame question, but if you have more of these expensive works, as in your example, and they have parameters, how would you best incorporate it into there to like create a?
Sorry, the question was kind of far away. Can anyone help repeat?
If you had more expensive words.
Works, I mean, if the expensive work had parameters, here it was, everything was the same, but if there were.
What would it be like if the expensive work had parameters?
So how would you best incorporate it into?
Sorry, I kind of missed that last part. Can you help repeat?
Sure. So if the expensive work had parameters, how would that change any of this?
Oh yeah, absolutely. So you would essentially, I mean, this example is a pretty cool example. Typically, you would have like you would like namespace requests. So you would say like, oh, this request. Oh, I mean, this example. I mean, in general, this idea of an in-progress cache only works if you're performing the same computation. So if you're performing the same exact expensive computation, then this works. If they are different computations, then yeah, of course, this wouldn't work. So that's what I assume if you're saying like if I have different parameters, yeah, so that wouldn't work. But in our case, in E2, for example, we have like validators that are trying to perform state transformation operations, the same exact operation, maybe like 1,000 times concurrently. So that helps us save a lot of time and just cycles. So yeah, it would change for sure if you have different parameters. Yeah.
Thank you.
Sweet. Thank you so much, Earl. I think that's all the time we got.
Great, thank you so much. I will be sharing the slides on Twitter and helping, posting the code. Thanks so much, guys.
Bye.
Thank you.